This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 156. Today's presentation is Rapid Burn Severity Mapping for Post-Fire Flood and Landslide Risk Awareness. Our presenter, Danielle Lozos, researcher from the Cooperative Institute for Meteorological Satellite Studies and Space Science and Engineering Center, the birthplace of satellite meteorology in Madison, Wisconsin. We're glad to have our facilitator today, Caitlin Rutt, who's a lead meteorologist at the Lubbock, Texas National Weather Service Forecast Office. As you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. Please post your questions in the chat and we will field them in the order they are asked. If you have not signed in with your full name, please specify your name when asking a question in the chat if we can follow up if necessary. Please also remember to check your spam folders if you're looking for TowerS communications. We've recently heard that some announcements for the Satellite Book Club and other TowerS mailers have ended up in there, and we don't want anybody missing the great content from our TowerS team. We're always looking for future presenters for the Satellite Book Club, so if you have a presentation coming up for the National Weather Association annual meeting and you'd like to repurpose that for a Satellite Book Club seminar series, please get in touch with Kishad Bowman and Emily Maddox. We'd love to have you. And if you're looking for training material, please contact Brian Mata at the Office of the Chief Learning Officer for any questions regarding that. I'd like to thank our TowerS team, Kishad Bowman and Emily Maddox, for their endless support of our Satellite Book Club, doing all the work behind the scenes every week to deliver these awesome presentations. The Office of the Chief Learning Officer, the GOES-R JPSS programs, and our presenter and facilitator. Really appreciate everybody. And of course, we appreciate all of the attendees that join us each and every week, including today. Without further ado, I'd like to introduce Danielle a little more formally. Danielle is a post-bachelor researcher working at SIMS SSEC in Madison. She got her start in Earth observations through a lucky placement as a Noah Hollings Scholar to work for the GOES-R Pro team in Greenbelt, Maryland. She much preferred this job over Zoom University and stayed on with the Pro team for the entirety of the year. In 2022, she graduated from Yale with a bachelor's in environmental science and has worked at UW-Madison since. She splits her time between two projects, modeling terrestrial carbon dioxide uptake from the GOES-R satellites and developing a multi-sensor tool which maps the burn severity of wildfires. Today's presentation. Danielle, welcome to the book club.
Thanks so much, Jordan. It's really a pleasure to be here today. I know I'm presenting to folks here in the building at SSEC and also NOAA people and general audience from around the country. So it's really exciting that you all joined this morning to hear what I'm up to. And with that, I will jump right in. I am presenting today on rapid burn severity mapping, and the purpose is for post-fire hazard awareness. So those include landslides and flood risks. And before going forward, I'd like to thank my supervisor, Sam Batsley, especially for all of his support of this project. All right, so wildfires are just as big of an issue as they've ever been between the Canadian smoke all summer and the latest tragedy in Maui, which we're seeing here as a Sentinel burned area map taken just a few days ago. You can see Lahaina on the left here is really strongly affected all the vegetation in that area, and then other burns from across the island. And so there's no more important time than right now to map wildfires well for a whole host of applications. And so today I'll be talking about the more specific motivation behind this project, as well as a couple research inquiries that I'm studying right now. And then I'll explain a bit about a burn tool that I've been developing on a cloud-based platform that is user-friendly. And I'll talk about the direction this project is heading, which is a very exciting direction because there's lots of collaborators and certainly lots of interest in improving our ability to quickly map burn scars. So a little bit more about these post-fire risks. So wildfires strip the ground of vegetation, leaving the soil very vulnerable to erosion and also leave it hydrophobic, so that when water falls from the sky in heavy precipitation events, you can have really damaging runoff, which can compound into flash floods, landslides, and debris flows. And those issues are certainly exacerbated in areas with steep terrain. And so weather forecasting offices and hydrologists have to map the intersection of precipitation forecasts and burn scars in order to know where these hazards are going to be most felt. And so here's an example of the status quo as we know it. It's certainly very different across weather forecasting offices, but here's an example from a team in New Mexico, and this shows a hand-drawn burn perimeter that's a pretty rough estimate of where the wildfire is, with no delineation of burn severity, whether it's high severity or low severity. And so we're hoping we can improve upon this sort of map to use the data that's at our fingertips with NOAA satellites to do a better job mapping these quickly and in a way that's accessible to end users like folks in weather forecasting offices. So this is the existing framework for mapping burned areas. So you have a wildfire ignite, and then the first GOES image is available almost instantaneously, within minutes, and then that day you might get a VIIRS image as well. But you'll have to wait a little longer for a higher resolution satellite image like Landsat or Sentinel. And the teams at the USGS, the Burned Area Emergency Response teams create bark maps, which take a difference between pre-fire images and post-fire images to create a burn severity map. And these pre-fire images and post-fire images can come from Landsat or Sentinel, but they have to be clear sky in order to see the burn underneath, because we're using passive radiometers that are detecting surface reflectance of sunlight. And so you're not going to have an easy time seeing through clouds and smoke. And so waiting for Landsat and Sentinel to get a clear sky pass of the burned perimeter can take a really long time. And it depends on the fire. Sometimes you'll get lucky within days, like we did in Maui, but sometimes it can take much longer, especially in areas that stay burning for weeks, months, and the chance of rain can happen at any time. The precipitation doesn't wait till the fire is 100% contained. So that's where we have this data latency gap that we're hoping to fill. And so for this audience, I'll cruise right through this, but today I'll be talking about the GOES-R satellites, especially imagery from GOES West, which was GOES 17 and is now GOES 18, and from the Advanced Baseline Imager, and especially looking at CONUS scans, which take place every 5 minutes. And then I'll also be talking about VIIRS imagery, and VIIRS is the radiometer aboard SUMI MPP, NOAA 20, and NOAA 21. which are polar orbiting satellites. And then I'll also be talking about burn perimeters, and I'm gathering my wildfire data from 2 different interagency programs operated at a federal national scale. So BEAR, which is the Burned Area Emergency Response Teams, their goal is emergency response. And so their goal is to create a map as quickly as possible using the most recent Landsat or Sentinel scan. And then once it's safe, they send ground teams in to evaluate soil burn severity and create maps that are called BARC maps. And then on the other hand, we have monitoring trends in burn severity, MTBS, and this program has more of a historical framework where they're looking at wildfires dating back to 1984 from the beginning of the Landsat record, and they're mapping all of these fires in really high detail, but it takes several years before the perimeters are released publicly. And so it's more looking at regrowth over time rather than being a good source for instantaneous maps. But both of these archives are helpful for me to use as more like ground truths for the VIIRS and GOES imagery that I'll be looking at. I'm also going to be talking about cloud-based computing, and one cloud-based server that I enjoy using a lot is the Google Earth Engine, which is a petabyte scale archive of satellite imagery that is accessible with just a few clicks and just a few lines of code to tap into their data archives and to do your cloud-based computing instantaneously due to the co-location of this storage archive with their APIs and servers, where you can analyze, visualize imagery all in one place. So it's really convenient. It uses parallel processing, which is high speed, and it's planetary scale. So it's really useful for this particular application where we're dealing with a vast amount of imagery over large scales. But there's certainly drawbacks of Google, and one of those is that it's limited to whatever data sets they decide to upload to their servers. So they do draw numerous GOES products from Google Cloud, but not all of them, certainly not all of them. Now, how do we map wildfire burn severity from satellite imagery? I'll be using the normalized burn ratio, which is an industry standard vegetation index that takes the difference between a post-fire image and a pre-fire image to see the change in normalized burn ratio over time. Now, the normalized burn ratio is a normalized difference between between near infrared radiation and shortwave infrared radiation, and that's the 0.8 micron band and a 2.2 micron band. And yeah, together that shows really well how live vegetation reflects strongly in the near infrared, but then post-fire you have a more dark burned surface, which is reflecting much stronger in the shortwave infrared. So this index is good at picking up that difference. All right, so now getting into the meat of it, which is that we can create these normalized burn ratio difference image, that's DNBR, with multiple satellites. Any satellite that has a 0.8 micrometer band and a 2.2 micrometer band is suitable to do this calculation. And so luckily we have many of those at our disposal, publicly available through NOAA and NASA. And we can see that there's a huge variety in how spatially coarse this imagery is. When we're using GOES, it depends on the band, but for me, that will be between 1,000 meters and 2,000 meters, for VIIRS 375 to 750, and then Landsat 30 meters and Sentinel 20 meters. And then we also have a big difference in return interval, so we're getting some images a lot more frequent than others. So this is a quick overview of how I get from an image to a burn map. So for GOES, I'll start with a start date and an end date. Those are user inputs. And from just those dates, we can get a collection of pre-fire GOES images and post-fire GOES images, say a week before and a week after. Now, since a CONUS GOES image is available every 5 minutes, the mean is, we're going to use a daily mean across all those GOES images so that we're not looking at way too many, and we can compare to other satellites that only capture one image per day. So I take a mean pre-fire, and then post-fire, I'll often take a mosaic where the most recent image is actually preferentially treated, where we want the most recent satellite imagery, so that image reigns superior, and the other images that are less recent are used in case of cloud or smoke obstruction. And so when we subtract our pre-fire and post-fire image, we get our GOES delta NBR image. And we can zoom into our region of interest to see what that looks like on a smaller scale. And we repeat that exact same process with VIIRS, Landsat, and Sentinel. And that's how I get 1, 2, 3, 4, a standard way to treat all of these satellites. Now to my current research, and this is really exciting because I've just started working on answering some of these tough questions. And the first is, how accurate are burn severity maps produced by GOES and VIIRS? And here's an example of the fire we were just looking at, which is the North Complex from 2020 in California. And I'm doing, some kind of validation calibration, not the official kind, but the type where I'm just wondering how similar are these two maps. And what we get in this particular case is a strong correlation, positive correlation of R equals 0.82 with a bias close to 1, which is ideal. Now, how about we expand that to 480 pre-fire and post-fire scenes? Well, let's see. First, let's eliminate all the scenes that have over 50% cloud cover. Now we're looking at 320 scenes, 332. And this is a diagram that shows some results. We're seeing the correlation between the GOES and VIIRS imagery plotted against the fire perimeter area. So we can see at larger areas, the accuracy is certainly higher, but low areas, it's really all over the map. Our correlation average is here only about 0.44. But making some adjustments, now we're only looking at fires greater than 50 square kilometers or 12,000 acres, and there's significant improvement. And then if we look at fires greater than 300 kilometers squared, which is essentially a mega fire, that's certainly a lot better as well, correlation of 0.69. And if we terrain correct our GOES imagery, now we're looking at a strong performance of a strong positive correlation of 0.77. And I'll pause for a second to discuss terrain correction. So I'm sure many of you all are familiar with the parallax effect, and that is due to the off-nadir view angle of the GOES satellites. So the greater the view zenith angle, or the farther away your target is from the equator, the more high elevation targets will be perceived as displaced by the satellite. And so their perceived location will be kilometers potentially away from their true location. And that is a huge issue when we're talking about surface phenomena that you need to accurately geolocate. And so what's really exciting is there's a lot of work at SSEC to improve GOES terrain correction for earth science applications. So Chris Schmidt, who's presenting next week, has developed some really exciting mathematical formulas to calculate the true pixel locations. And I've implemented that in Earth Engine. So here's a Mullen fire, which is in the Wyoming Rockies. And we can see this is the GOES imagery, uncorrected and corrected, on top of Sentinel imagery and the burn perimeter. You can see that burn perimeter aligns well with the Sentinel imagery after it's been terrain corrected, which is hugely exciting and really important going forward. And so here's some preliminary results across all 4 of these satellites, where we can see most of these pairs have correlation around 0.7, and biases that are not exactly 1, because the different sensors have are differently they have different wavelengths, and so they're more sensitive to certain wavelengths than other sensors. And so we're not going to have all, especially Landsat has a slightly different bandwidths, and so it's going to behave differently than VIIRS. And so when you're looking at all 4 of these, you're going to need to correct for those systematic errors. Now, the other very important question is, why bother? Can GOES and VIIRS produce burn maps significantly quicker than Landsat and Sentinel? And I am here to say yes. This is what I'm currently working on, and so this is really new, but it's definitely promising to see. So this is looking over time at how this North complex fire developed and was seen by different satellites. So we see on September 7th, you're seeing nothing from GOES and smoke and clouds from VIIRS. And then over just a few days, the fire blows up in size, which we are seeing in our GOES imagery, which is taking a composite across every 5 minutes of GOES imagery throughout the midday. And so GOES is able to see this burn perimeter, while VIIRS is still obstructed by smoke and clouds during its pass. And we get a Landsat image on the 10th, where we're seeing just the corner of it, but mostly it's cloud obstructed. And then same with Sentinel on the 11th. And so that whole week, GOES was the only satellite able to really figure out what was going on beneath those clouds and smoke. And then the next week, this is actually a case where VIIRS gets pretty unlucky, and it's not really seeing the perimeter either until about the 15th. And on the 16th, we have a beautiful Sentinel pass, and we can finally map this fire really well in high resolution. But at that point, it's been 10 days since the fire blew up in size. And so if there's a heavy rainfall event before then we're out of luck unless we're able to use some of these coarser resolution satellites. And so here's a more quantitative look at cloud cover over time. And so that's cloud or smoke obstruction, where the GOES composites are only at most about 14% cloud obstructed, whereas VIIRS, you're getting an image each day, but often it's cloud obstructed. And then here we have 3 Sentinel passes, which aren't clear enough until day September 16th. And Landsat does not actually see this fire well until the 26th of September. All right, and so next, I'm going to do a really quick demo of this burn mapping tool that I've created to help users interact with this data. And here's a link. I can drop that in the chat later, but this is a prototype hosted on Google Earth Engine, designed for anyone without background in satellite imagery to use. And what all you input are a start date, an end date, and an area. And what you can get out is a continuous raster that shows DNBR as a geotiff, or a vector that shows discrete burn severity classes as a GeoJSON. And these are GIS-compatible formats that are designed specifically for hydrologists. And so this is what the app looks like if you go try and play with it. You're welcome to. Here I'm selecting, let's see, there we go. I'm selecting VIIRS as the satellite. I'm keeping the default baseline start and end dates to look at that North Complex fire. And I checked 8-day post-fire composite to look at an 8-day mean of VIIRS imagery. And this is in real time. It's doing this calculation over 8 days. It's showing me a small thumbnail of what it will look like in this region of interest. And then I can click to download a raster or a vector data. And so there's certainly plenty of work to be done with this app, but it's a great starting point for users to really interact with these different options and see which satellites are providing the best outcome. Now, eventually, this will be a multi-sensor endeavor where we'll be fusing together the best and most timely pixels from all 4 of these sensors to create a best possible map at any point, so that whoever's looking always has the best data to make their predictions about post-fire hazards. And what else? All kinds of things we're working on. I'd love to publish this work and refine this app and address inconsistencies between the satellites. I am on a team of several folks, including my supervisor, Sam at SSEC, and Roger Michaelides and Javier from the Weather Prediction Office. And we're all working together to create this multi-sensor fusion product that we will have tested by hydrologists at the weather forecasting offices and hopefully implemented. We're talking with the NOAA fire weather test bed as well. And we're excited that we've received a NOAA grant to keep this work going for the next 2 years and hopefully deliver some results that are ready to be used by the whole community. And I should mention that Roger, what he's contributing is using some active radar SAR from Sentinel-1 and fusing that with our passive imagery in order to help see through clouds when you don't have any imagery, even from GOES. And so that's going to be really useful. for some of these thick smoke scenes. So yeah, that's all I have. I'll turn it over for questions now. Thank you all.
Thank you, Danielle. So I just want to remind everyone to stay on for a little bit of discussion. And I encourage everyone from the field forecast offices and regional headquarters to put your full name in the chat when you are asking a question, so we know who you are. Also, check out the chat for a feedback survey. Should be posted there shortly. And in about a week from today, so on Thursday, August 24th at 12 p.m. Eastern Time, Chris Schmidt, researcher from SIMS and SSEC, will discuss satellite applications for fire weather. Also, feel free to contact the Tower S team, Kashad Bowman and Emily Maddox, if you have any questions about the Satellite Book Club or for configuration of satellite products. And so now we'll move on to some questions, and I'll get the questions started here, and then I believe we have a few in the chat. So I'll start off. Will you integrate active fire detection into the burn mapping tool? I think you're muted there, Danielle.
Perfect. Thank you. Thank you for the question. And so that's really important because there's a lot of work being done in active fire right now, especially with the GOES fire product. And it's really important that these things work together. So the team here at SSEC is developing a dashboard to help people find the active fires and all of the information we have associated with them. I would love for ultimately this tool to be linked to that interface so that you can take the active fires and then see the burn maps, which are not looking at thermal infrared radiation or the amount of heat being emitted from the fire, but it is looking at the effect on the vegetation and how severely the ecosystem's being burned. So these things are separate, but definitely important to look at together. And I would also love to use the GOES active wildfire detections to improve the confidence of these burn severity maps so that we can see that that pixel was burned for a certain duration before we assign it a value of its burn severity. So there's definitely a lot of work to be done to integrate the active fire and the burn severity mapping.
Awesome, that sounds great. Thank you, Danielle. So we do have a question from Tim Schmidt. He said, great talk. Any idea how much more accurate burn scars would be from the next generation GOES imager, so GXI on GeoXO, given its VIS and near IR spatial resolutions from 250 to 1,000 meters?
Right. So that's I'm really looking forward to seeing this GXI imagery because from GOES, which is at about 1,000 meters, down to VIIRS, there's already a huge improvement in what you can discern in that map. So it's going to be very important, a really important advancement coming up. But I think even better than a high resolution map is being able to look at smaller fires. You can see GOES is not accurate with fires under 50 square kilometers. And so I think we'll see that number drop way down to hopefully much smaller fires will have an accurate burned area maps.
Awesome. It looks like you got a bunch of great talks, good presentation. I'm not seeing any other questions. Oh, looks like one might have just came in from James Nelson. Are there any plans to do difference mapping from week to week? And he also added vegetation regrowth work.
Right, thank you for that question. In a given week, you have lots of images captured by GOES and probably 7 by VIIRS. and that provides ample data to be able to do any sort of week-to-week mapping. Vegetation regrowth work, often you're looking at the same season from year to year. And so the app I created provides ultimate flexibility for a user to select what data they want to look at. So you could actually set the pre-fire date as November 2019, even if the post-fire date is in December 2020. And so you can look between years and see how the burn scar is developing over time to do that vegetation regrowth work.
Awesome, thank you. We have another question that came in. Brian Mata asked, how does this imagery compare to the Maxar imagery?
This imagery is much coarser. If you were following the Maui wildfires this week, the New York Times published satellite data imagery on the front page the day of or the day after using Maxar imagery, which, correct me if I'm wrong, but I think it's about 1 meter. And so that is way different because you can see building level destruction, and that's really exciting that we can map buildings in high resolution and see what's happening right after the wildfire. But unless you have the resources to purchase this Maxar imagery, that's going to be pretty inaccessible for most people, and it's not, and so we have the option of all of these other publicly available data sets, which can provide coarser imagery, but just as timely imagery, and it's still extremely useful.
All right, it looks like we have potentially a question or a comment from Andrew Orson. It says, great talk, Danielle. Having an ability to integrate these satellite-derived burn maps in a timely manner could be extremely helpful to mesoscale operations at the National Weather Service level and for them there at WPC, for their MetWatch desk in issuing any kind of mesoscale precipitation discussion product. Anything to highlight fresh burn scars, their scale, and potential severity can be very helpful for assessing these small scale but potentially significant burn scar related flash flood threats. So it sounds like a kudos, and this product might be really helpful in our operational fields. And there is a question here from Alexandria McCombs. Any plans to automate the drawing of burn perimeters and burn severity to be used operationally?
That's a great question. Right now, this is, the least amount of information possible, which is where we're just asking a user to sketch the general area where they think this burn scar is to get the output map. But that said, it still is a user input, and it won't always be possible to know where that burn scar you're looking for is. So I think down the line, there is a lot of potential to use something like the SSEC active fire dashboard, which will have a latitude and longitude of the fire ignition as a starting point, which would be sent to these servers, and you could get a normalized burn ratio map of that region based on the latitude and longitude. As much as I would love this Earth Engine app to become operational, through a bit of work with NOAA, I know that they have a lot of procedures and contracts with different types of organizations, and so it's not always possible to just integrate every tool you create into the National Weather Service. So I think ultimately an app or an interface would need to be designed in conversation with NOAA to create the sort of experience that they're contractually allowed to publicize everywhere. So I'm not sure if it will be this app, but it's certainly a great prototype for what a user experience might look like in the future.
Awesome. Thank you, Danielle. And I think that's all the questions that came in the chat, and we're coming in on our closing time. So thank you again, Danielle, for the great presentation. Looks like a lot of people did enjoy that, and I will turn it back to Jordan for his final remarks.
Thank you so much, Caitlin, and thank you so much, Danielle, for that excellent presentation. And thanks to everybody for joining us today. As has already been mentioned, the Satellite Book Club continues next week, the normal time, 12 noon Eastern time. We're going to continue the discussion of satellite applications for fire weather with another one of my colleagues from SIMS SSEC at UW-Madison. In the meantime, if you have any questions for the Tower S team, please reach out to Kashad Bowman, Emily Maddox. They are here to help, so please don't hesitate to contact us regarding the Satellite Book Club or anything related to the configuration of satellite products. With that, I hope everybody's staying cool this summer. Hopefully you're taking a little vacation when you get a chance, and hope to see you again next week. Take care, everybody.